Astronomers have discovered a highly magnetic neutron star called a magnetar, which appears to have a lot of the characteristics of those mysterious high-energy pulses known as fast radio bursts. Neutron stars are created when very massive stars, far larger than the Sun, reach the end of their lives and explode in powerful events known as core collapse supernovae. What's left behind is a highly compacted superdense stellar corpse, so tightly squashed that all the positively charged protons and negatively charged electrons are literally crushed together to form neutrons, hence the star's name. Although only a dozen or so kilometers wide, neutron stars are the densest objects in the universe other than black holes. Fast radio bursts are mysterious sudden high-energy flashes at very specific wavelengths, lasting just nanoseconds and originating at cosmic distances. Most are singular events, occurring just once at a specific location in space, and then never again. That suggests they're probably caused by some sort of cataclysmic event, such as a supernova. The problem is there have been several fast radio bursts which have repeated, and these appear to originate from near the centers of galaxies. And the speculation suggests they're caused by the supermassive black holes that reside there. Now, scientists with Caltech and NASA's Jet Propulsion Laboratory in Pasadena, California, have analyzed fast radio burst-like pulses coming from what appears to be a magnetar located near the supermassive black hole at the center of the Milky Way galaxy. One of the study's authors, Aaron Perlman from Caltech, says these observations are showing that radio magnetars can emit pulses with the same characteristics as those seen in some fast radio bursts. The authors were studying a magnetar named PSR J1745-2900. It's located near Sagittarius A star, a supermassive black hole at the center of our galaxy, some 26,000 light-years away, with a mass of some 4.3 million times that of the Sun. PSR J1745-2900 was initially spotted by NASA's Swift X-ray Space Telescope. It was later determined to be a magnetar by NASA's NuSTAR, or Nuclear Spectroscopic Telescope Array spacecraft. That was in 2013. Magnetars are a rare subtype of a group known as pulsars. Pulsars, in turn, are rapidly spinning neutron stars. Magnetars are thought to be very young pulsars which are spinning more slowly than ordinary pulsars and have much stronger magnetic fields, which suggests that perhaps all pulsars go through a magnetar-like phase during their lifetime. PSR J1745-2900 is the closest known pulsar to the supermassive black hole at the center of the galaxy, separated by a distance of just 0.3 light-years. And it's the only pulsar known to be gravitationally bound to the black hole and the environment around it. All of this has allowed scientists to use this magnetar to help probe the conditions and environment near the Milky Way's supermassive black hole. In addition to discovering similarities between the galactic center magnetar and some fast radio bursts, the authors also gleaned new details about the magnetar's radio pulses. Using one of NASA's Deep Space Network's largest radio antennas, located at Tidbinbilla near Canberra in Australia, scientists analysed the individual pulses being emitted by the star every time it rotated, a feat that's actually pretty rare in radio studies of pulsars. They found that some pulses were stretched or broadened by a larger amount than what was predicted when compared to previous measurements of the magnetar's average pulse behaviour. Furthermore, the behaviour varied from pulse to pulse. Speaking at the 233rd meeting of the American Astronomical Society in Washington, Perlman says he was seeing these changes in the individual components of each pulse on very fast timescales. And the behaviour is really unusual for a magnetar. The radio components are separated by only 30 milliseconds on average. Now, one theory to try and explain the signal variability involves clumps of plasma moving at high speeds near the magnetar. Perlman and colleagues suggested the movement of these clumps could be the actual cause of the observed signal variability. Another theory proposes that instead of something happening to the magnetar, the variability is intrinsic to the magnetar itself. Perlman says understanding the signal variability will help future studies of both magnetars and pulsars at the center of the galaxy. Perlman and his colleagues are also hoping to use the Deep Space Network dish to solve another outstanding pulsar mystery. Namely, why there are so few pulsars near the galactic center. Their goal is to find the non-magnetar pulsar near the galactic center black hole. Perlman says finding a stable pulsar in a close gravitationally bound orbit with Sagittarius A star could prove to be the holy grail for testing theories on gravity. If they find one, they'll be able to do all sorts of unprecedented tests of Albert Einstein's general theory of relativity.